the lines 1 and line 2 have equation x plus a over 2, 5 minus y over 2 and equals to z plus 1. This is line 2, alpha of 6 negative 4 1. Right, so find the angle between line 1 and the z-axis. As well as let's look at the first question. To find an acute angle between line 1 and z-axis, we know that this is very straightforward. It's just an application of the formula. So what we do is we need the direction vector of the line as well as the direction vector of the z-axis. So given our line 1, alright, the issue is that line 1 is not really if we were to observe our line 1 carefully, it is not is the Cartesian form, and it's not easy for us to identify the direction vector of the line. Is what we do is perhaps it will be better for us to set this up in the parametric form so that we can identify the direction of the line better. Okay, so I'm sure by on your own effort you would have been able to rewrite the equation of line 1. So this should obtain you that you should have negative 8, 5 and negative 1 plus lambda of 2, negative 2, 1, where lambda is real, and this would actually be the parametric equation alright, of the equation of line 1. Alright, and for the z-axis, well, basically for the z-axis, you know that if you recall, this is the z-x, this is the y, and z-axis. If I want to find a direction vector that goes in the direction vector of the z-axis, one simple very direction vector would just be 0, 0, 1, right? Because basically we're not going anywhere in the xy direction, but we're going one unit in the z direction. So very simple direction vector is just to use 0, 0, 1. Okay, with that, we actually have the two direction vectors. One is the direction vector of the line. One will basically be the direction vector of the z-axis. Okay, and with that, let's do our part 1. So we want to calculate the acute angle between line 1 and z-axis. So what we do is I'll just take a cosine theta, right, equals to the modulus of direction vector of line 1 dot product with vector parallel to the z-axis. Right, take the magnitude of the direction vector for each, and with that, you know, you should be getting a modulus of 1/3, and theta because cosine theta is equal to 1/3. Now just do the cosine inverse and final answer will turn out to be 70.5 degrees. Alright, so we are done with basically part 1. Okay, let's look at part 2 now. Now we will look at the position vector of the foot perpendicular from the origin, okay, to line 1. Now if you recall, right, line 1 basically right, we are looking at the foot origin, or foot of perpendicular, sorry, from the origin all the way to line 1. So line 1, as we have written earlier, okay, is basically negative 8. Alright, just copy it here again. And we are finding n, right, which is the foot of the perpendicular. Now this is a very standard foot of the perpendicular question. Basically what we're doing, the classifying on the topic is that the foot of the perpendicular from a point to a line, right? So if you're not sure, you just go to the notes and you actually revise this category, the relationship between a point and a line. So we are finding the foot of perpendicular. What we do is we're going to use the fact that the direction vector of ON and the direction vector of the line is going to give us a dot product of 0 because they are perpendicular. Okay, so what I want to find for ON, because ON basically n, you know that is something special about this point n is that it lies on the line. Okay, so it actually lies on the line. Right, so one thing special is that, you know, if ON lies on the line, this ON can be so-called written in the form of the line. So ON, right, can be written as negative 8 plus, it can take the form of the line. Okay, for a particular value of lambda, it can take the form of the line. okay, for some lambda. It's not for all, it's for some lambda. And it turns out that because in this case we are looking at the four perpendicular from the origin to the line, ON is basically this. Alright, this is also basically the ON. So in this case, ON is also a direction vector lah. Okay, it's also a direction vector in this case. And if you look at the direction vector of line 1, this is basically lambda of, okay, this is 2 of negative 1. So retrieving these two, alright, I know that if I dot product ON with the direction vector of line 1, I'm going to get 0 because they are perpendicular. Okay, and just solve this by yourself. Okay, I'm sure you'll be able to obtain that lambda should be equals to 3. Alright, you should be able to obtain the answer that lambda equals to 3. And what do you get from this? Is that basically you just need to take, you know that lambda is equals to 3, just take this and sub it back here, and you're going to get your ON. So hence, just sub lambda equals to 3 into ON, and you obtain that your ON is equals to -2, -1, 2. Alright, and you have finished your part 2 easily, which is the four perpendicular from the origin to the line 1. Okay, part 3, we need to find the point of intersection between line 1 and line 2. So here again, if you are doing part 3, the point of intersection between line 1 and line 2 goes like this. So this was our line 1. Alright, so our line 1, basically the equation looks something like that. Right, which you have done earlier. Line 2 was this. Right, so in order for us to find the point of intersection between these two lines, all we need to do is just basically solve simultaneously. And remember that if you solve simultaneously, the one that we are going to use here, sorry, just let me write this also, is basically the R. Alright, we acknowledge that R is basically the substitution that we're going to create in both cases. Now don't forget that this R, right, they're actually the same. It represents x, y, z. Alright, x, y, z is a position vector of any point on the plane. So at the point of intersection, right, basically the point of intersection must fulfill both the two equations. That means for the x component for line 1 is -8 plus 2l lambda, and the x component or the I component for L2 is basically 6 alpha. Okay, and you have 5 plus -2 lambda, equating the j component. You equate the k component, and you have equation 1, equation 2, equation 3. So what I basically do is just solve for lambda. Alright, so remember, you can't use a GC for this, you gotta do it manually. Just do it and solve. I mean, okay, all goes well, your lambda should be equals to -12, and your alpha should be equals to -3/2. I'm not going to bore you with the trivial, solving Sponge equation, because those are secondary school. You should be able to do. Okay, with that, after you have the fact that lambda equals -, you can just take either one of them, just sub it back here or here, and you can get the point of intersection easily. So the point of intersection, alright, the point of intersection, basically the point of intersection, your answer should turn out to be, let's say if I were to sub alpha, right, so it's basically like 6 of -3/2, -4 of -3/2, and -3/2, and your answer will turn out to be -9, 6, and -3/2, because you are finding the point of intersection, not a vector. You're finding a point. So I'm going to write it in a row form. Okay, next, so we just got to look at the last part, which is to find the vector equation of the reflection of line 2 in line 1. Okay, so if you remember the line reflection, so this is part 4. part 4 requires us to find the vector equation of the reflection of line 2 about or in the line L1. So if you recall, let's try to draw maybe we draw line 2 first, and we draw line 1, and we try to observe what are things that we found. So part 2, we know that the position vector of the foot of macular from the origin to line 1, right, is basically 2, which is n, actually -2, -1, 2. Okay, and you realize that one thing, interesting thing is that the origin, okay, if you observe, right, it actually lies on line 2, right? Because remember for the equation of line 2 is actually 6, -4, 1. Now if you observe this equation carefully, you realize that actually the origin does lie on line 2. So that's a very beautiful thing. Alright, and the point of intersection here is basically P, which is -9, 6, and -3 is also found by you in the earlier portion. We are looking for the equation of the reflection of line L2. Okay, let's just call this L2 prime, or the reflected line in the line L1. Right, so what I need to do is probably for this particular line, maybe what I do is I kind of need a position vector, which I do have, and I also need a direction vector, which I do not have at the moment. So we're going to find a direction vector, right? Maybe what I can do is I can create a point, look for another point here. Maybe I just look for first, what I can do, I can I find the reflection of maybe the origin in the line L2. How about that? Okay, so actually it's very interesting because, well, if I want to find so-called, let's say, if for example, if I call this an n prime, right, then you can see that the reflected, because the ratio here, right, if you were to look at the ratio here, right, it's basically 1:1, but the ratio is just 1:1. So if you think about it, and on prime, okay, O of n prime, actually basically it's just 2 of on. Okay, so if you do use ratio theorem or whatsoever, it will still get garner you the same answer. On prime is basically -4, -2, and 4, and this point basically is -4, -2, and 4. Okay, there's a difference between me writing it as a coordinate and compared to as a position vector here. Okay, because this is on prime, which is 2 times of on. Okay, and to find the direction vector of this line here, right, basically now I have 1 point and 2 points. Okay, I'm ready to create my direction vector. Alright, so Pn, let's just find Pn prime. It's basically on prime minus op, which is -2, 4, subtracting my op. Alright, and your direction vector should be basically half of, let me just simplify it, 10, -6, and 11. Alright, this gives you the direction vector of the reflected line, right? The direction vector. So what I have found here is the direction vector of this line, the reflected line, right? With that, we're almost done. So actually for part 4, basically the answer is just the reflected line. Answer would just be position vector plus the direction vector. Alright, and we are done with the last part of question 6.